Just 1 minute. Oof. Is the material visible? No. Well, is the material visible?
Yes, sir.
Visible, sir.
So next, technique of discretization of analog filter. This is known as bilinear transformation. Right. Just recall the exact relation between Z and S. Z is equal to e to the power S tau. Therefore, S is equal to 1 by tau natural logarithm of Z. There is a version mismatch, so that's why here a box has come in. This should actually be approximately equal to 1 by tau natural logarithm of Z, approximately equal to 2 by tau 1 minus Z to the power minus 1 by 1 plus Z to the power minus 1. If you expand natural logarithm of Z into an infinite series and truncate the series after the first term, then you will get this approximate relation between S and Z. So this relation is known as bilinear transformation or two-steen transformation relation. Therefore, based on this approximate relation between S and Z, what we can do is that, how does it help us in obtaining an equivalent digital filter for any continuous time filter? Simply in the expression for GS of the analog filter, replace S with 2 by tau 1 minus Z to the power minus 1 by 1 plus Z to the power minus 1. So you will get the transfer function of an equivalent digital filter. Now, this bilinear transformation relation, we have also seen that it can also be obtained by comparing the transfer functions of an ideal, that means a continuous time integrator, and a discrete time trapezoidal integrator. What is the transfer function of a continuous time integrator? It's 1 by S. All right. And what is the transfer function of a discrete time trapezoidal integrator in the Z domain? It's tau by 2, 1 plus Z to the power minus 1 by 1 minus Z to the power minus 1. That means 1 by S can be considered to be approximately equal to tau by 2 times this term. Or S is approximately equal to what is written here, 2 into 1 minus Z to the power minus 1 divided by tau into 1 plus Z to the power minus 1. So the same relation can also be obtained in this way. All right. That's why this method of discretization of analog filter, this is also known as trapezoidal integration method. Write down this part.
Hello, sir.
Yes.
Sir, someone is not able to enter the class. Can you please say
I've
to?
allowed several of them just now.
Okay, sir, sure. Thank you, sir.
But whenever I do that, it's very difficult to go back to this Word document. I cannot see the Word document right now. So again, some to write down this one part. I cannot go on allowing in this way. You cannot enter the class whenever you like. One by tau natural logarithm of z, that should be equal to, approximately equal to, this box. There was some version mismatch of the equation editor, so this is actually approximately equal to. Bilinear transformation method is an extremely important method for discretization of analog filters. Comparison of the two transfer functions also yields this bilinear transformation relation. That's why the method is also known as trapezoidal integration method. Have a look at equation 3 now. From equation 1, we obtained that z is approximately equal to, what was equation 1? That is equation 1. From this equation, if you rearrange the terms, you will get an expression for z. Z again here, this is approximately equal to 2 by tau plus S divided by 2 by tau minus S. Or it's equal to 1 plus tau by 2 into S divided by 1 minus tau by 2 into S. Here, just substitute sigma plus j omega for S. Replace S with sigma plus j omega in equation 3. Then what would you get? On making that substitution, Z will become equal to 1 plus sigma tau by 2 plus j omega tau by 2 divided by 1 minus sigma tau by 2 minus j omega tau by 2. If that is the case, then what will be the expression for magnitude of Z? Just root over. In the numerator, you have root over 1 plus sigma tau by 2 whole square plus omega square tau square by 4. In denominator, you have root over of this term. So only difference between the numerator and denominator is here you have a positive sign, here you have a negative sign. That is the only difference. All right. Then how will the different regions in the S plane map onto the Z plane in accordance with this approximate relation between Z and sigma and j omega? What will be the relation? Just see that while I am trying to let you enter into this meeting, I am not able to go back to the Word document. Is it visible? So what can you say? If you consider three cases, sigma less than 0, sigma equal to 0, and sigma greater than 0, what will happen to the magnitude of Z? If you have a look at this term, 1 plus minus sigma tau by 2 whole squared, this is 1 plus sigma squared tau squared by 4 plus minus sigma tau. Therefore, now if you consider three cases, when sigma is less than 0, what is written on the left-hand side will be less than what is written on the right-hand side. The left-hand side appears in the numerator, the right-hand side appears in the denominator. So if that is the case for sigma less than 0, correspondingly what will happen? The magnitude of Z, it will be less than 1. All right. If you substitute sigma equal to 0 here in this expression, substitute sigma equal to 0, magnitude of Z will come out as 1. If you substitute sigma greater than 0, what will happen? what is written on the right hand side, that means this one will be greater than left hand side. That means in this expression, magnitude of z, it will be greater than 1. So I repeat that sigma less than 0 means magnitude of z less than 1. Sigma equal to 0 means magnitude of z equal to 1. And sigma greater than 0 means magnitude of z greater than 1. All right. It means that the j omega axis in the S plane maps onto the circumference of the unit circle centered at origin in the Z plane. Now, sigma less than 0 means magnitude of Z less than 1. Implication is that if GS has a pole in the left half of S plane, the image of this pole in the Z plane will be inside the unit circle. Therefore, causal stable continuous time filters will result in causal and stable discrete time filters if you carry out discretization by this bilinear transformation technique. We made the same observations in case of the exact relation between S and Z. Now we are considering uh, an approximate relation between S and Z. So apparently the observations appear to be same. But is it really so, or there is any subtle difference? Let us try to examine. First, write down this part. Since we are deviating from the exact relation between S and Z and opting for an approximate relation, everything cannot be same. I should have written here, therefore, if sigma is less than 0, then this equation holds good, and under that condition, magnitude of z is less than 1. So some if should come here, if sigma is less than 0. And here, if sigma is equal to 0, magnitude of z is 1. If you just concentrate on the mapping of the j omega axis, when we considered the exact relation between S and Z, what happened? Whenever you cover a span of omega S along the j omega axis, the unit circle centered at origin in the Z plane, it was traversed once. There was one complete traversal of the circumference of the unit circle centered at origin in the Z plane. So when you sweep along the j omega axis from omega equal to minus infinity to omega equal to plus infinity, the circumference of the unit circle that was traversed infinite number of times. Therefore, every point on the circumference of this unit circle, that is the image of infinite number of points on the j omega axis in the S plane. As a matter of fact, every point in the Z plane is the image of infinite number of points in the S plane. So that is the reason why aliasing of characteristic took place when we considered the impulse invariant transformation, which is nothing but the application of standard Z transform. To understand the intricacies of this transformation method, we describe a phenomenon that takes place here that is known as frequency warping or distortion. When we design any filter, what property of the filter gives you idea about the behavior of the filter? Obviously, the frequency response. So here, let us try to compare between the frequency responses of the analog filter under consideration, which has been discretized, and the frequency response of the equivalent digital filter. So the analog filter frequency response is G j omega, while the discrete time filter frequency response, that is Gd e to the power j omega prime t. So small omega, G with argument j, small omega. So this small omega is the frequency in the analog domain, and capital omega prime is the frequency in the digital domain, both in radians per second. So let us try to derive a relation between small omega and capital omega prime. You may wonder that why am I representing the two frequencies by different symbols? Well, if there is no logic in such representation, small omega and capital omega prime, they should come out to be same. Then we may understand that, well, there is no logic. Otherwise, if the expression is different, they are not equal, there is every reason to represent them by two different symbols, and that will indicate that there is a distortion in the frequency response. So that is the rationale. In the expression,
একটা প্রশ্ন আছে স্যার, বলছি যে একটা সিগন্যালকে যদি ডিসক্রিটাইজ করি তাহলে তার ফ্রিকোয়েন্সি রেসপন্সটা স্যার পিরিয়ডিক আসে, তো স্যার ফ্রিকোয়েন্সি রেসপন্সটা
স্পেকট্রামটা ফ্রিকোয়েন্সি রেসপন্স হয় না, ফ্রিকোয়েন্সি রেসপন্স সিস্টেমের হয়, স্পেকট্রামটা বলো।
হ্যাঁ, তো স্যার ওইটার পিরিয়ডিসিটিটা স্যার টাও এস হবে না 2π হবে? মানে আমি যদি ওমেগা এস ফ্রিকোয়েন্সিতে
যদি তুমি রেডিয়ান্স পার সেকেন্ডে কনসিডার করো ফ্রিকোয়েন্সি, তাহলে পিরিয়ডিসিটিটা হবে ওমেগা এস অথবা এফএস যদি হার্টজে কনসিডার করো। আর যদি ডাইমেনশনলেস কোয়ান্টিটি হিসেবে কনসিডার করো, রেডিয়ান্সে তো এক্সপ্রেস করা হয় অনেক সময়, কারণ ডিসক্রিট টাইম সিগন্যালের ক্ষেত্রে রেডিয়ান্সে এক্সপ্রেস করা হয়, তাহলে ওমেগা এস মানে কি? ওমেগা এস মানে হচ্ছে 2π। 2π পিরিয়ডিসিটিটা 2π হবে সেই ক্ষেত্রে।
স্যার ওমেগা এস ইকুয়াল টু 2π ইনটু এফএস, তাহলে শুধু 2πটা কোন সেন্সে বলছে?
যদি ডাইমেনশনলেস কোয়ান্টিটি হিসেবে এক্সপ্রেস করো, তাহলে ফ্রিকোয়েন্সিটা হয়ে দাঁড়াবে ওমেগা এস ইন্টু টাও। এইটা ফ্রিকোয়েন্সি হয়ে দাঁড়াবে, অ্যাঙ্গুলার ফ্রিকোয়েন্সি। ক্যাপিটাল ওমেগা এস দিয়ে যদি একে রিপ্রেজেন্ট করো, তাহলে ওমেগা এস ইন্টু টাওটা কি হচ্ছে? কিন্তু তোমার কথা অনুযায়ী ওমেগা এস ইন্টু টাওটা তাহলে 2π দাঁড়াচ্ছে না? ওমেগা এস মানে কি 2π বাই টাও।
2π বাই টাও, হ্যাঁ।
ওমেগা এস ইন্টু টাও মানে 2π, সেই জন্য 2π হচ্ছে।
আচ্ছা স্যার।
যদি এটা হবে যদি রেডিয়ান্সে এক্সপ্রেস করো ফ্রিকোয়েন্সিটা, রেডিয়ান্স অথবা রেডিয়ান্স পার স্যাম্পল একই জিনিস। টাওকে ওমেগা এস এর মধ্যে অ্যাবজর্ব করে নেওয়া হচ্ছে। Now in the expression relating S and Z, you replace S with J small omega and Z with e to the power J capital omega prime tau. This was the relation. On making those substitutions, what you get is written here in equation 6. J omega is 2 by tau 1 minus e to the power minus J omega prime tau, J into capital omega prime tau, divided by 1 plus e to the power minus J into, here there is a mistake. Here it should be capital omega prime. Actually, in my lecture, I represent frequency in radians by capital omega. So that's why I have used a different symbol here, capital omega prime, to represent frequency in radians per second. So here it should be capital omega prime. So here also prime, there also prime, obviously same. Therefore, in the numerator and denominator, if you just multiply the numerator by e to the power j into half into omega prime into tau, and denominator by the same expression, then you get this expression. Here also omega prime. All right. Now in the numerator, if you divide the numerator by twice j and multiply by twice j, what will you get? What will happen to the numerator? It will become twice j into sine capital omega prime tau by 2. All right, dividing the numerator by twice j and multiplying by twice j. That is what is written here. In the denominator, if you multiply the denominator by 2 and divide it by 2, it will become 2 cosine omega prime tau by 2. All right. So these two and these two in the numerator and denominator, they will cancel out. So j into small omega will become j into 2 by tau into 10 omega prime tau by 2. So that is, this relation is known as frequency warping relation. This is one of the frequency warping relation. You can also write in this way, omega is this one. You can also write that capital omega prime, the digital frequency in radians per second, it will be 2 by tau, tan inverse small omega tau by 2. All right. So these two relations are known as frequency warping relations, and they indicate a gross distortion between small omega and capital omega prime. All right, write down this part. তোমাদের প্রফেসর পাল যে ক্লাস নোটগুলো পাঠিয়েছেন সেখানে দেখবে যে যখন when the z transform of a sinusoidal signal, sinusoidal discrete time signal, causal sinusoid that was evaluated, then first you consider the sequence as sine omega tau, omega n tau. All right. Then you absorbed tau into omega. So that became capital, the sine of capital omega into n. There was no independent time parameter, time variable present there. So if you represent the sequence as sine of capital omega into n, what is the unit of capital omega? That is radians or radians per sample. So that is the reason. এই যে আমি বললাম যে স্মল ওমেগা এস ইজ 2 পাই, ওই সাইনোসয়েডাল সিগন্যালে ক্যাপিটাল স্মল ওমেগার সঙ্গে টাউকে একসঙ্গে ক্লাব করে ক্যাপিটাল ওমেগা পাওয়া গেল। ক্যাপিটাল ওমেগার ইউনিট হচ্ছে তোমার রেডিয়ান্স। তাহলে স্পেকট্রাম যেটা, দ্য স্পেকট্রাম দ্যাট ইউ গেট অফ দ্য ডিসক্রিট টাইম সিগন্যাল, it will be periodic in small omega s or fs. Or if you want to express the frequency unit in radians, the periodicity will be twice pi radians. Small omega is radians per second, or twice pi radians, or fs hertz. This will be the period of the spectrum. So be careful here in equation 6. I have made some, there is a slip. You should write capital omega prime here and here. What will happen at very low frequencies? Tan capital omega prime tau by 2, it will become approximately capital omega prime tau by 2 if that this, because the unit of capital omega prime tau, that is in radian. So tan capital omega prime tau by 2 will become approximately omega prime tau by 2 at low frequencies. Therefore, small omega and capital omega prime, they will become approximately equal at low frequencies. So except for very low frequencies, a gross distortion between small omega and capital omega prime takes place. As a result, the frequency response of the analog filter gets considerably distorted when you change over from the analog filter to the equivalent digital filter, except for very low frequencies. So this is actually the plot between small omega and capital omega prime tau. As capital omega prime tau tends to pi, small omega tends to plus in infinity. As capital omega prime tau tends to minus pi, small omega tends to minus infinity. So you can see here that no two values of small omega can have the same value of capital omega prime tau. That means if you just consider every value of capital omega prime over this range, minus pi by tau to plus pi by tau, then every value of capital omega prime, it is the image of a single value of small omega. Single value of small omega. Therefore, here the aliasing of characteristic does not take place. All right. Aliasing of characteristic does not take place in this transformation technique. So what will happen when small omega is minus infinity? What will be capital omega prime? It will be minus pi by tau, or capital omega prime tau, that will be minus pi. Similarly, as small omega becomes tends to plus infinity, capital omega prime tau, it will be pi. So now just try to see here that when you start traveling along the j omega axis from omega equal to minus infinity, here in the z plane you were there, because omega prime tau, that should be minus 1 minus pi. So minus pi means angle is measured in this way. That is the zero position, 0 degree. So from 0 degree minus pi. So you were here. So as you travel upward along the j omega axis, you will be traveling in this direction. In this way, when you reach omega equal to 0, you will be here. If you continue your march and move on to the higher and higher values of positive values of omega, you'll be continuing your journey along the circumference of the unit circle. And ultimately, as omega tends to infinity, you will come back here. So one complete traversal only. As you sweep along the j omega axis from omega equal to minus infinity to plus infinity. So aliasing of characteristic does not take place here. That is an advantage of this method, but the baseband frequency response, the original frequency response, it becomes grossly distorted, not because of characteristic aliasing, that is absent, but because of a nonlinear relation between small omega and capital omega prime. Draw this figure. এখানে একটা কি যেন ওভারল্যাপ হয়ে গেছে, দাঁড়াও 1 মিনিট। ইয়েস। Now every point on the circumference of the unit circle centered at origin in the z plane, it is the image of a single point on the j omega axis. That is the reason why characteristic aliasing is absent in this transformation technique. With a simple example, in the next part, I have tried to illustrate the effect of frequency warping. just see here that I have drawn a typical arbitrarily chosen amplitude response of a continuous time filter. This is the small omega axis, and that is the magnitude of Gj omega axis. So this is an arbitrarily chosen amplitude response of a continuous time filter that is being discretized by bilinear transformation. So in the next figure, I have drawn here, the y-axis is small omega and x-axis is capital omega prime tau. So as you can see that for low frequencies, it's almost linear, and distortion becomes more and more severe as capital omega prime tau approaches pi units, and small omega tends to infinity, plus infinity, as capital omega prime tau tends to pi. So if you just have a projection of the salient values of omega here and here, I mean, take the projection and come back here. So what will you get? A frequency response of this form. So that is a compressed version of the frequency response of the continuous time filter. So this is the frequency response of the digital filter that you obtain by bilinear transformation. So see how distorted is that one. So draw this figure. Have you drawn it? To overcome the effect of frequency warping, we introduce what is known as frequency pre-warping before application of bilinear transformation technique. So what is the procedure involved? Let us see. Just recall that when you apply bilinear transformation, you change over from small omega to capital omega prime. So what happens? Distortion takes place according to equation 7, or you may say distortion takes place according to equation 8, truly speaking. So from small omega, you get capital omega prime. So distortion, as you move from analog filter to digital filter by bilinear transformation, distortion takes place in accordance with this relation 8. Therefore, prior to application of bilinear transformation, if we can apply a distortion to the critical frequencies in accordance with equation 7, then what will happen? We do intentional warping of the cutoff frequency, the stop band age, etc., according to equation 7, and then the transfer function of the analog filter that we obtain with these new frequencies, that is subjected to bilinear transformation. So in the course of applying bilinear transformation, distortion will take place in accordance with 8, just the reverse distortion. So the pre-distortion, pre-introduced distortion, and the distortion that will take place due to bilinear transformation, they nullify each other, all right, at frequencies close to the critical frequencies. So that is the idea involved. So come to bilinear transformation and frequency pre-warping. To write down these parts which I have already pointed out. First, desired critical set of digital filter corner frequencies, capital omega 1 prime, capital omega 2 prime, etc. They are determined from the specifications given. So you apply the frequency warping relation to get small omega 1, small omega 2. Capital omega 1 prime is converted to small omega 1. Capital omega 2 prime is converted to small omega 2. So with this new set of critical frequencies, you obtain the order of the filter. If not already stated, you obtain the order of the filter, and consequently, you obtain the analog filter transfer function. Then you apply the bilinear transformation. I have here enumerated the steps. The steps to be followed, they have been enumerated one by one here. So what will be the first step? The desired critical frequencies, capital omega C1 prime, capital omega C2 prime, etc. of digital filter to obtain analog cutoff frequencies, small omega C1, small omega C2, small omega C3 in accordance with the relation that is written here. So this is the pre-warping step. So that is the first step that I have pointed out. All right. In the second step, you obtain the transfer function GS of a suitable analog filter with these cutoff frequencies, new set of cutoff frequencies. Then you transform GS to GDZ by applying bilinear transformation. So these are the three steps involved. Write down. The specifications that will be provided to you are the intended specifications for the digital filter that you will ultimately obtain. Remember that. Not of the analog filter. So these are the specifications meant for the ultimate digital filter. In impulse invariant transformation, you consider those critical frequencies as analog filter critical frequencies because you have no other way. You have to do that. Similar is the case for that approximation of derivative technique. But here, from the desired digital filter cutoff frequency, you get the warped analog filter cutoff frequencies. Then using those cutoff frequencies, you obtain the order of the filter and then the analog filter transfer function. You have written this part. Now I have considered here a very simple example. Have a look at this example. You have been asked to design a first order digital low pass filter with a cutoff frequency of small a radians per second, obviously, and DC gain of 1. Remember that in any filter design problem, if the DC gain is not specified, you have to consider it as 0 dB or 1. For a high pass filter, if nothing is mentioned about the high frequency gain, you have to consider it as 1 or 0 dB. Anyway, so here the DC gain is given as 1. So here the desired cutoff frequency of the digital filter is A radians per second. So what will be the watt cutoff frequency of equivalent analog filter? It's small a1 equal to 2 by tau tan a tau by 2. So transfer function of first order analog low pass Butterworth filter with this cutoff frequency a1 and a DC gain of 1. What will be that transfer function? 1 by 1 plus s by a1. That means a1 divided by s plus a1. In place of a1, I have written here 2 by tau tan a tau by 2 here and there. All right. Now you have to apply the bilinear transformation. Application of bilinear transformation means in this expression for GS, you have to replace S with 2 by tau 1 minus z to the power minus 1 by 1 plus z to the power minus 1. So this is the application of bilinear transformation. Just see here that in the numerator and denominator, this 2 by tau, this term is common. This is an interesting thing. In the numerator, that 2 by tau term, and in the denominator, in the second term, which contains 2 by tau, this 2 by tau and that 2 by tau, they have crept in while we pre-warped the desired digital filter cutoff frequencies. That was the result of appearance of those 2 tau terms was the result of this bilinear, this frequency pre-warping. In this term, the 2 by tau term has come in. Why? Why has it come in? It is because of the bilinear transformation relation that has been substituted here. So all these 2 tau terms, they will cancel out. So GDZ will come out as tan a tau by 2 divided by 1 minus z to the power minus 1 by 1 plus z to the power minus 1 plus tan a tau by 2. It can be simplified further. You have to simplify it further and obtain the transfer function. But I have not done that because it's simply an algebraic process. But what I wanted to point out here is that this 2 by tau in the numerator and denominator, they have cancelled out. This is not a mere coincidence. The 2 by tau arising from the application of frequency pre-warping and from the application of bilinear transformation, they cancel out. This is a general phenomenon. All right, irrespective of the type of filter that you design, this thing will take place. Therefore, for practical purposes, not an exact relation, it is sufficient to consider when you are applying bilinear transformation preceded by frequency pre-warping, it is sufficient to consider small omega as tan capital omega prime tau by 2 and s as equal to 1 minus z to the power minus 1 by 1 plus z to the power minus 1, because 2 by tau that is supposed to be present here and 2 by tau that is supposed to be present there, both these 2 by tau terms, they will cancel out. Now, as a consequence, just try to understand this thing. Often the desired digital filter cutoff frequencies, they will not be specified in radians per second. They will be specified in radians. Specified in radians means you will not be provided with the value of omega prime, omega 1 prime, omega 2 prime, etc. But you will be provided with the value of omega 1, capital omega 1, capital omega 2, etc. Capital omega 1 means the product of capital omega 1 prime into tau. Capital omega 2 means the product of capital omega 2 prime into tau. So instead of giving the digital filter critical frequencies in radians per second, they can be given in radians. So if that be the case, because we have seen that it's not necessary to use 2 by tau in these relations, therefore, for frequency pre-warping, the relation that should be used is 10 times capital omega prime, which includes tau inside it. All right. And here also 2 by tau is not required. Here also 2 by tau is not required. That means in that type of problem, it is not necessary to have a knowledge of the sampling frequency or sampling rate. Be careful about that. If you are given such a problem, you will raise a hullabaloo that if you have not prior knowledge, you may wonder that why this sampling frequency information is not provided. All right, write down this part. now have a look at another issue. What we have described just now, it was that the specifications were given. The desired digital cutoff frequencies were made known to you. Then you did the frequency pre-warping, etc., and then applied the bilinear transformation. Instead, the problem may come up in this way also, that a particular analog filter transfer function GS may be available to you, and you may be required to obtain the equivalent digital filter transfer function by bilinear transformation. If you straightway apply the bilinear transformation on this GS, what will happen? The effect of frequency warping will be there. Therefore, you have to apply frequency pre-warping. But how to do that? Remember that the transfer function GS, if you want to obtain the equivalent digital filter, what will be the equivalent digital filter critical frequencies? The equivalent digital filter critical frequencies will be same, are expected to be same as the analog filter critical frequencies. How are the analog filter critical frequencies obtained? From the location of the poles and zeros. Recall your knowledge of Bode plot. They are the breakpoints. They determine the breakpoints. So those analog filter poles and zeros, they are to be pre-warped first, because ultimately you desire a digital filter with this analog filter critical frequencies as their own frequencies, own critical frequencies. So instead of directly applying the bilinear transformation, first you have to pre-warp the analog filter critical frequencies. So every real pole and zero represented by S plus A, all right, that has to be converted into S plus A prime, where A prime is 2 by tau tan A tau by 2. That is the first step. I am talking about if straightway the expression for GS is given to you. For complex poles and zeros, you have to convert the second order terms of this form into the form specified here, where omega n prime is 2 by tau tan omega n tau by 2. So from GS, you obtain a modified transfer function GS prime, GSA prime. All right. Now you apply bilinear transformation. GDZ, it will be GSA prime with S replaced by that expression. But remember here that in this case, when you are moving from GS, given GS via bilinear pre-warping, via frequency pre-warping, then application of bilinear transformation, your amplitude scaling is not automatic. Preserving the DC gain is not automatic. If the filter under consideration is a low pass filter, preserving the high frequency gain is not automatic if the filter under consideration is a high pass filter. So you have to introduce a scaling constant K to preserve either the DC gain or the high frequency gain, as the case may be. That's what I have written down in this step 3. Amplitude scaling is not automatically satisfied and must be considered separately. If DC gain has to be preserved, we evaluate the filter's constant. By now, I don't know whether you have knowledge. How would you obtain the DC gain of a digital filter? A discrete time LTI system from the given GDZ, how will you obtain the DC gain? Simply by replacing Z with 1. In the expression for GDZ, if you substitute Z with 1, you get the DC gain. Why it is so? In the expression for any GS, you have to substitute S with 0 to get the DC gain. And because Z is e to the power S tau, therefore, obtaining the DC gain of GdZ is simply substituting Z equal to 1. In case of high frequency gain, you have to substitute Z equal to -1. Because for obtaining the high frequency gain in case of analog filters, you have to substitute omega equal to infinity. But in case of discrete time filters, the maximum discrete time signals, the maximum frequency of interest is omega s by 2. So what is the corresponding Z? E to the power s tau. That means e to the power j omega s by 2 into tau. That means e to the power j pi. E to the power j pi means -1. Therefore, for any transfer function GdZ, the high frequency gain is obtained by replacing Z with -1. So in this way, you may match the DC gain of the analog filter and the digital filter, or the high frequency gain of the analog filter and the digital filter, as the case may be. So write down this part. হয়েছে? Have a look at this example. Again, a very simple example. Just see that you have been given an analog filter transfer function Gs equal to A by S plus A, and you have to determine the equivalent digital filter transfer function by applying bilinear transformation preceded by frequency pre-warping. So here that term S plus A, the first order term, it determines the critical frequency. So S plus A is to be converted into S plus A prime, where A prime is 2 by tau tan A tau by 2. So that's what I have done here. The numerator does not contain S. So here there is no question of converting A to A prime. Simply terms involving S. So that is done. All right. Remember that GS, the expression that is given, it's a first order analog low pass filter. So the DC gain of this filter is to be preserved. So now once you get GS A prime, you apply the bilinear transformation relation. So S is replaced by 2 by tau 1 minus z to the power minus 1 by 1 plus z to the power minus 1. So what do you get then? This one. GdZ will be given by this expression, and K has to be evaluated so as to preserve the DC gain of the analog filter. The DC gain of the analog filter was seen to be unity. And so we desire that the digital filter also should have a DC gain of 1. DC gain of the digital filter is obtained by replacing Z with 1. So you get the DC gain of the digital filter as written on the left hand side, this term. So that should be equal to 1. So K should come out as 2 by tau tan A tau by 2 by A. On making that replacement for K here, what do you get? You get GdZ as given there. So that is the final form of GdZ. So write down this example. Quickly write down these properties of bilinear transformation preceded by frequency pre-warping. Stable GS transforms to stable GDZ. There is no aliasing of characteristic. Amplitude response of GDZ matches amplitude response of GS at very low frequencies that was there, plus now near pre-warped critical frequencies. So that's the uh, the merit of using bilinear, the frequency pre-warping. the phase response is distorted. And it's easy to apply because no factorization of the numerator or denominator polynomial is necessary, and therefore no partial fraction expansion is also necessary. Impulse response, because you have deviated from the exact relation, the impulse response is not preserved. And phase response is also distorted since frequency response at omega equal to infinity is compressed to capital omega prime equal to pi by tau. So that completes our theory for designing of IIR filters. So now the only thing left is considering certain problems, numerical problems. So when can we meet next? Saturday morning? Say something.
Sir, actually, on 13th we have class test from 10 to 11:30.
Oh, if it's not inconvenient for you, I can meet in Saturday afternoon also. Say around 3 o'clock or something like that.
No, sir, in the evening also there is a class
The class
test of
test.
BJB, sir.
Okay, then when? Monday is
Sir,
15th.
Sunday will be okay for you.
Sunday will be okay for me, no problem.
Sir, we have till now we have no class test on Sunday, 14th.
So Sunday at what time?
Sir, 10:30.
Okay, so that is fixed. Sunday at 10:30.
Okay, sir.
Okay. So after you write down, let me know. I'll log out. বলে বলো।
Yes, sir, done.
So let me just stop recording and then log out.